So we have to link a few concepts we already got introduced to. So we have saying there is inertial instability, and we talked about perpetual instability. So there is always propagations of absolute vorticity across the equator, creating inertial instability and the convection, secondary circulation, and so on, which means there must be transients in the ITCZ. So what are the transients like, and how does it affect the heating, the circulation, and the secondary circulation, and so on? Reminding ourselves again about the easterly waves. This is July-August of 1967. You can clearly see the multi-scale structures, as they are often referred to, more straight up latitudinal arrangements versus these easterly propagating systems. So this is, when you have high resolution data, you can always draw these phase lines and look at clusters and different directions of propagations, different time scales, and so on. But to derive them actually or to reproduce them in the models is not always that straightforward, as we already know. Again, another reminder, the transients in the ITCZ are again shown as part of the OLR variance for June, July, August, and September, October, November in the quasi-biweekly time scale, in the what is called a high frequency intraseasonal time scale, so 10 to 20 days, and the low frequency intraseasonal time scale, which is the 20 to 60 days. Obviously relative frequencies, but especially in the monsoon region, it becomes very critical to separate these time scales and look at the active and break periods and so on, which we'll come back to later on. Okay, so looking at the character of the transient, we'll just again go through some descriptive details based on this reanalysis data. This is all from characteristics of the mean 1981 to 2000 June, July, August meridional circulation. We are looking at the Eastern Pacific and the Central Western Pacific. We know that those are very different regions. So this is 120 to 110. Mistake here. Actually, let's go back to 13.7 and look at the section. So we are going to look at mass stream function and relative humidity to see how the troposphere gets charged up, and we are going to discuss locations P and M. So there is P on this side and M on this side that are discussed in the text. Eta equal to 0 line is shown here in both cases, and we know that wherever there is weak cross-equatorial pressure gradient, you end up with this situation where there is the absolute vorticity line, 0 line, sticking to the equator in the summer season, and basically in other seasons as well, depending on whether the ITCZ is crossing and the cross-equatorial pressure gradient is changing seasonally. Okay, but let's focus on the mean circulation first for this long-term mean, and you have mass stream function showing the rising motion with relative humidity being advected way up into the upper atmosphere by the upward branch of what we have been calling the Hadley cell, but we are now calling it the ITCZ, same thing. And the main thing is again to remember the advection of absolute vorticity across, creating inertial instability. So eta or F is less than 0 over here, and you have convection happening to the north of this 0 line, and you have the corresponding circulations over here. So this is when you look at the full circulation, the total mass stream function, we will see a bigger cell that we have typically looked at when we do the Hadley cell. Okay, the situation from the east to the west is dramatically different. The equatorial region here is the cold tongue. The equatorial region here is warm. So you can see somewhat of higher humidities, and there is a subsiding motion here with a secondary cell that has happened or is supplying the subsiding branch here, and the upward branch here is weak, but you can still see the upward advection of humidity. When you look at divergence and relative humidity, you can see the divergence convergence doublets that we talked about, and relative humidity. So you can see the divergence being shown in these red lines and black lines. Okay, so not much to say other than to say that this is all consistent with what we have seen before. Where there is strong cross-equatorial pressure gradient and advection of relative humidity, we have strong convection. So this is something to remember. And we have the divergence convergence doublet, and then we have the vertical structure. So the question is now to look at the evolution of some of these things at short time scales to give us a sense of the transients that we are interested in. So this is one way to do it. We are looking at days and latitude averaged over this longitude band, again in the Eastern Pacific and the Western Pacific, east of the date line. And you can again see the evolution of daily values of anomalous OLR, which are shaded in watts per meter squared on this scale here. And you have absolute verticity zero line being shown here, and the negative minus 15 10 to the minus 6 per second line here, and the plus 15 10 to the minus 6 line over here. So clearly, again, this is day 150, which is around May, going through day 740, which would be end of August or so. You can see the transients clearly in terms of the OLR anomalies. So the low OLR anomalies obviously are the convective phases, and the red regions have positive OLR anomalies with respect to the low frequency that has been extracted out. So that's the dry phase. So you have this excursions of the zero absolute verticity line corresponding to the convective phases, low OLR, showing also the other side, the equatorward side of the convection, which we talked about in terms of the secondary circulation, which is also contributing to ameliorating the inertial instability. The central western is very different. The absolute verticity line is basically migrating across the equator, not going too much farther into the northern hemisphere, and the positive verticity line is stuck here as well. And you have equatorial precipitations happening also on these various high frequency timescales, which correspond to the maps we saw of the OLR variance at different time bands, from synoptic to quasi-biweekly to the 20 to 60 days and so on. Okay, gives you a good sense of the synoptics. If you do 4 to 8 day filtered latitude time sections, then again this latitude time plot, which are called Muller diagrams, as you probably know. This is looking at OLR and the 925 hectopascal relative the absolute verticity change, and there is a strong correspondence between the advection of the relative verticity and these propagating features. So time is going this way, so they are propagating northeastward. Okay, so all kinds of features are there, which is again very different. Here you have some higher frequency variability in the 5 to 10 degree north band, whereas the convection was mostly stuck on the equator here. So you have lower frequency evolution and higher frequency transients happening here. So this is consistent with what Holton was saying about various propagating features. Okay, this is 4 to 8 day bandpass filters. So this is just the divergence term that we talked about, which is required for vorticity balance at the eta equals 0 line that we talked about in terms of splitting into divergent part and rotational part, and we explained how the divergent part is going to go to 0 near the 0 absolute vorticity line, and the rotational part is going to give us these strong westerlies. So even the divergence shows these high frequency variabilities with somewhat of a propagating feature. Looking at the upper level, 250 hectopascal, you see that there is a equatorial and ITCZ level propagation or high frequency features which correspond to the secondary circulation that we talked about, right? So you need the equatorward side of the convection features that are related to the main convergence, divergence, and the secondary convergence and divergence. Again, different at the western part corresponding to this. So my main point would be that the ITCZ is not monolithic. It's very different, even in the Pacific itself. It's very different in the east and the west, and actually we haven't looked in detail in the middle yet. Okay, so let's leave it here and look at the transient composites in the next podcast. But the main message is that the perpetual instability and the high frequency time scales we would expect if there is perpetual inertial instability being generated by cross equatorial incursions of vorticity advection, then it is confirmed by these transients in the ITCZ itself, which is of course transients in the convection.